Let's see. Okay, this is the paper that I'm going to present. Here's the link to it. And this is the title. It's a practical paper, I believe. So I will begin with the next slide. Just the abstract that I think is an important way of looking at it. The paper is concerned with classification using only a limited number of training examples. And the method that they call it, they name it RN for Relation Network. And it learns a deep distance metric using a data set that's not directly related to the target classification problem. So we'll talk a little bit more about the importance of that. But if it was directly related, then you would probably just use that database. The important aspect in the paper, they want a disjoint data set. So this RN can be used to compare an unknown sample to a known set of examples. And it will find the most similar example, and its label is then used as the unknown samples class. So in a sense, it's a best match. And the paper does extensive experimentation, and they show that it works well. Some of the terms that they use in the paper that we'll learn about that I think are kind of unique to it, perhaps. Few shot learning, meaning only a few examples are used to train the system to learn. C-way K-shot, C being the number of classes and K is the number of examples in the class. An embedding module and a relation module. Modules can be thought of as just a function. In practice, in this paper, they are a network composed of processing nodes. So the paper brings this up. I'll summarize this. I think it's we go into a lot of detail, but I'll just say quickly that deep learning networks work very well, but they need many examples of each class, probably because they have many parameters, and the complexities of the data can be represented using all these parameters. But there are lots of practical problems that involve small data sets. So learning with a deep network will overfit these data sets and will not generalize well. In contrast to deep learning networks that may require a lot of data, humans do well on classifying tasks using only a few examples. you can show a child a picture of a zebra, perhaps just a single picture of a zebra, and they'll be able to pick out the zebra from images. So that would be one-shot learning. So the paper goes into quite a bit of detail on past efforts in this few-shot learning area. But generally, they tend to be very complex, and they require sophisticated inference algorithms and also time-consuming fine-tuning of an existing network. The relational network classifies data by first embedding the query in the sample images and then comparing them with a relation module. So both the embedding module and the relation module are meta-learned from a related data set that is independent of the training set. So by meta-learning, we're implying a kind of transfer learning. So we're not learning the model directly, but in a higher level fashion. Some related work that they mentioned, fine tuning. So that's using an existing pre-trained network and then using the smaller database to tune the parameters of the network. They mentioned recurrent neural networks with memory. Those tend to be complicated, take a long time to train. Metric learning, which is training a network to produce embeddings that can then be, so that's learning projections, and then a linear classifier is used to make decisions. A Siamese network, that has a lot of similarities to this paper, I believe. So that would be training a network to produce embeddings that can then be used with a linear classifier. So I'll perhaps talk a little bit more about how that relates to this paper. So the relational network has advantages to all these approaches I just mentioned. It meta-learns on a large related data set, an embedding and a non-linear metric. So the non-linearity is important. And so it's an end-to-end training. It's simple and it's simpler and more powerful than these predecessors. So I just want to bring up a very, very simple way to build a classifier, the nearest neighbor search method. And so to build a classifier with this NN, we can simply take examples for each of the problem classes and embed them in a vector space. And the unknown, say what the paper frequently calls a query example, is also embedded. And the nearest neighbor is found and its class is assigned to the unknown sample. So the advantage is it's simple and fast, and the disadvantages are pretty important in that the embedding, it's not general, and it can produce a lot of false neighbors for the target domain, so it won't particularly work well. And then the distance metric tends to be simple, and it won't account for the complexities of the embedding space. So the relational network has advantages and disadvantages, and the big advantage is the embedding is general. It's learned on a large set of data, and that enables it to represent the data with a complex model that have many parameters and are less likely to be overfit. Another advantage is the relation module is learned in a nonlinear manner and allowing it to find matches that are better. So we'll talk more detail about what I mean by an embedding and a relation module. You may already know quite a bit about this, but I'll just go over it as an example of an embedding of an image in a vector space. So on the right, we have VGG16, which is available in a pre-trained form, and it can be used to embed an image in a vector space. And so, for example, if you put an image into it, which will need to be 224 by 224 and 3 color planes, it will forward propagate through the network. And at the very end, the VGG will return 1,000 outputs. So it can be used very simply to embed the image in a 1,000 dimensional vector space. If we go above that final layer, there's a layer above that which has dimension 4096. So that's another option of embedding. And then finally above that, there's another layer that has 25,088 dimensions. So this is an example of a network to embed images. The network in the paper is different than this, and we'll go over its architecture, but it's quite a bit simpler than VGG. So the relational network uses 3 data sets. It has a training set, a support set, and a testing set. So the last two, the support set and the testing set, they share the same label space. So all the examples are from a common set of labels. Whereas the training set, those labels are disjoint from the support and testing set. And so this is in contrast to a typical supervised learning task, where the training and validation and test sets all share the same labels. If you did share all the same labels, then you probably wouldn't use this technique, because then you could simply use the training set to build the model. So the terminology used in the paper is this C-way K-shot learning. And so, so that means that the training set contains C classes, and there's K examples of each. If we have a small training set, you could use a nearest neighbor classifier, but the performance will be poor. But by leveraging a large training set, its information can be transferred to this relational network, and it'll result in better performance on the test data. And the paper defines what they call episode-based training. This is analogous to building mini batches of examples that mimic this support and test set. And the mini batches are constructed from a random set of C classes from the training set using K examples of each class. So during each episode of the training, a new set of C classes are chosen and then are used to form this sample set and query set, which are then used to adapt parameters using an objective function, which we'll discuss. So the sample set and the query set are selected from the training set to simulate the support and test sets. So they're designed to have the same C and K that's available in these support and test sets. So here's a picture of the structure of the data. Maybe this is maybe a little bit simpler. So on the right-hand side, we have our test and support set. And I've kind of drawn this maybe in a tabular form, in a one-hot kind of encoded form, so that you can see that they're sharing the same labels. So the support set has only 6 examples from 3 classes, and they're 2 each, so we can call that a 3-way 2-shot. And the test set has random samples from those same classes. The query and sample sets are selected from the training data using these episodes. So we'll discuss a little bit about the algorithm that's used. But basically, it's an iterative algorithm. And episodes are like mini batches, and they're chosen to mimic our test and support vectors. And the notation that's used for the data is X and Y, X being, in this case, images, Y are the labels for the image, and I, the indice I in a paper typically is the sample, means the data comes from the sample, whereas J, indicates it's the query. So again, as I mentioned, that the labels from the training set are disjoint from the test and support set. And it typically might have many more labels than what the test and support set has. But the test and support set have the same labels. All right, so I'll move on. That's a picture of what I've been talking about. So this is another picture of the Relation Network's module transformation and how it's used. The module transformation. So the sample and query vectors, the xi and xj, those are both embedded into a vector space using the same function, this embedding module f(phi). And after the embedding is done, those 2 vectors are concatenated together. And then that concatenated vector is then transformed again with the relation module g(phi). And that transformation is what's called, produces what's called the relation score, Rij, between sample xi and query xj. And that's a real number, but it's bounded between 0 and 1. And so a 1 would indicate that the images are very similar, and a 0 indicates there's no similarity. So here's a diagram from the paper that I think is very good as well, and it displays the 5-way one-shot. So there are 5 classes on the left, which are color-coded with these squares to the very left, and one shot, meaning there's only one example of each. The query set is shown at the bottom in yellow. The indicator is yellow. So all of the query and samples are transformed. Whereas the query is concatenated with all the samples to form a larger vector, so it doubles the size of the vector. And then that undergoes this relation module transformation to produce a relation score. So one, even though this is a scalar transformation, because there are 5 inputs, we have a vector with 5 outputs. And if we one-hot encode that by picking the largest one, then that would indicate what that would be a classifier for the data. So what we want to do is learn the F and the G. And these are neural networks, so we'll use traditional deep learning techniques to estimate the parameters of those functions. So before I talked about how VGG16 can be used as an embedding, but this architecture they're using is quite a bit different from VGG. So this diagram, which is from the paper, shows both the embedding and the relational blocks. So I can just go through that and describe those. So in this diagram, the images are processed through the network, starting from the bottom. So images start here, and they have a specific size. So in the paper, they discuss primarily 2 data sets. That's omniglot, which are characters, and mini ImageNet. So omniglot is monochrome, and the images are 32 by 32 pixels. And mini ImageNet, I believe this is exactly the same as what's called CFAR 100. And they're 32 by 32 pixels, but they're color. So they have 3 planes of pixel information. So each one of these convolutional blocks are based on 3 by 3 filters, and there are 64 of those filters. And the convolutional block it's more than convolution. It also has batch normalization and rectified linear unit. So it has nonlinearity in each one of these blocks. So the embedding module, which is analogous to the VGG diagram that I talked about before, that would be these first 4 blocks before the feature concatenation stage. And the relation module are the blocks following the concatenation. So, talked a little bit about these convolutional blocks and how big they are. Some other things in terms of size. The last 2 green blocks are these fully connected layers. And so the first one is H by 8. So H is dependent upon the database that we're using. So if it's Omniglot, that is H is 64. Whereas if it's ImageNet, it's 64 3 by 3. So it's larger due to the color planes. But still, this entire fully connected network is small, much smaller than the fully connected network of VGG. So this relation score is a scalar, and you can see how this final network, fully connected network, it's only 8 units, and it has a sigmoid output, so that will map the inputs to 0 to 1. Whereas the layer before that's also fully connected, but it uses the rectified linear unit. So here is the algorithm for training, kind of broken down. So the outer loop is a training iteration. So this is very much analogous to the way we train deep networks with many batches. So within each iteration, we select an episode, which is basically a set of data to be used in that iteration. So the first part of that is to pick C classes from the training data. So, and C is the number of classes in the target data set. So that is typically much smaller than the data in the training set. And it's a random set of classes, which are, as mentioned before, they're disjoint from the target. But once you choose those C classes for the episode, then you pick data from those C classes. So the notation, as I mentioned before, is you have the sample set, which has C times K elements in it. So there's potentially K examples of each of the C classes. And the I index is used to differentiate that from the J index, which are the queries. So the queries are also chosen from the same set of C classes, but there doesn't appear to be any restriction on, they're more randomly chosen from those classes. So once the query and sample sets have been chosen, they can be used to adapt the parameters of the model, adapt the module parameters. And those 2 modules are the embedding and the relation modules. And so those parameters, those were just shown in the previous slide. Those are all these weights associated with these fully connected layers and all these weights associated with these convolutional blocks. So the adaption has several steps to it. The first thing is to compute the embeddings of all the data. So that would be taking all the images and running them through this first set of blocks. Then the relation scores are computed. So the relation scores are computed on the concatenation of those vectors that I just mentioned. So then that amounts to, this is running the data through the final stage, the G stage, the relations stage, to get these RIJs, which are numbers between 0 and 1. So then finally, the step 3 is the learning stage, where we adapt the parameters of the model. And we do that by minimizing the objective function. So the objective function is this summation of, on the right-hand side. This is not, so let me just describe the terms of the objective function. The Y's are the labels of the data. And so this equals, you can think that's just perhaps a Boolean. So, you know, are these labels, do they match or mismatch, true, false? And then this 1 takes that Boolean and turns it into a number, either a 0 or a 1. So that makes this, this expression compatible with the real numbers produced by the relation module. And so you subtract those two numbers together and square them. So basically it's MSE, mean squared error, is the metric that we want to optimize to do the learning. It's a little bit different than what's typically used, but you know, so it's, in some ways it resembles a regression learning. And so I've used this equation, this expression from the paper, and it's not completely correct in this step, because this argmid would imply that you're finding these parameters globally, whereas this step is really, it's a delta. You know, you're adapting these parameters, you're moving the parameters towards the minimum in a stepwise fashion. So in reality, you would use something like Atom, and you would use a learning rate. So this is not technically correct, but it's globally what you're trying to do. There are a couple of papers, excuse me, a couple of data sets that the paper uses in order to prove that it works. And I'll just describe. The first one is called Omniglot. And here's a picture of, you know, handwritten characters from an alphabet within Omniglot. So Omniglot dataset has 50 alphabets within it, and there are 1,623 total characters. And these are going to be the classes that we're concerned with in our model. So a class is a specific character. So each one of these characters or classes has 20 examples. So it's divided for the purposes of the experiments into 2 parts: a 1,200 character sample query training data set, and the remaining, you know, from the 1623, that leaves 423 characters for this testing set, which the support and test set, as it's also called in the paper. And there are 4 experiments that are documented. The 5-way one-shot. So 5 classes, but only 1 example. And the 5-way 5-shot. So we have 5 examples. So the 20-way, we have 20 characters that we try to choose from. And there's 1-shot and 5-shot versions of those. So 4 different experiments. So the summary of this is that the relational network, the paper that's described, the network that's invented and described in this paper, performs better than all previously reported methods, except it's tied, in a sense, with mammal on the 5-shot 5-way. And we'll look at those details in the next slide. We can look at those. So here are the omniglot experimental results. So these are accuracies. These numbers are accuracies, and they're averaged over 1,000 episodes. And these plus minuses are the confidence interval, 95% confidence interval. So the dark black is the best score for that experiment. So the RN is, the very last line, and has all the dark black numbers, except for the one in the 5-way 5-shot column, where it seems to be better, 99.9, mammal did better than the 99.8, but the confidence interval, if we add the 0.1 to that, we'd get 99.9, and if we subtracted 0.1 from this, we'd get 99.8. So these are overlapped. So in a sense, there's not much confidence that mammal is better than the RN. So another experiment that is performed in the paper is mini ImageNet, which I believe is what I've called CFAR 100. So it has 60,000 images from 100 classes. So it's balanced, perfectly balanced. So if you divide that, you would get 600 examples per class. So for purposes of the experiment, we divided into 64 classes for training and 20 classes for testing. So again, this is disjoint. There's also 16 classes that are used for validation. So the total of 64, 20, and 16 add up to the 100. But these are kind of just held out and used for monitoring generalization. So 64 and 20 are kind of the classes that we've talked about before. So in this set of experiments for mini ImageNet, they only look at the 5-way 1-shot and the 5-way 5-shot. And the result on that is that it performs better than all previously reported methods on the 5-way one-shot. However, it's not the best on 5-way 5-shot, but they say that it is competitive. So if you look at the column in the paper, it's not the best, but it's in the top 2 or 3.
Frank, just want to understand the 5 classes. They're not in the test set or which set are they coming from? The 5 classes that they've chosen?
For the 5-way class, that they would be coming from the 20 classes here
for the testing. Okay.
Yeah.
Got it.
So, so far I've mainly talked about. I haven't talked about zero-shot learning. I'll just kind of describe that. He goes. That's part of the paper. Goes into quite a bit of detail on zero-shot learning. I don't know if I'll have time to do that today. However, I thought I'd just give the definition of that. It's to start with ZSL, zero-shot learning. That's when you set K to 0. So you don't have images to be used as examples. So the sample images are replaced by categorical descriptors of the image. Here is an example from AWA. That's animals with attributes. You can find that on the internet. And so here are some images of polar bears. And here are attributes to the left. So attributes there's 6 attributes listed: black, white, brown, stripes, water, or eats fish. So the polar bear is not black. No, it's white. It's not brown. It does not have stripes. Water is yes. And eats fish, yes. Whereas the zebra, the same set of attributes, it has different indicators on those attributes. And I think this is kind of interesting. You know, the colors black, white, brown, it actually it is black and it is white, but it's not brown. And stripes, that's obvious. And water, you know, some of these are sort of ambiguous, but you know, the polar bear you might associate water with highly, whereas the zebra, no. Eats fish, probably, definitely not. So that's that's a description of this, these attributes for this data set. And let's see. So the AWA, there are 30,745 images from 50 classes of animals. So it's in the experiments broken up into 40 training classes and 10 test classes. And this attribute vector that I just described, rather than 5, they have 85 attributes that they've assigned to each of these 30,000 plus images. So the results that I'll just briefly summarize are that it is superior to all other methods except for this SAE and DEM. So So let's, moving into a little bit more of a description of how things work. The important things about it are that the relational network is both a deep embedding and a deep nonlinear metric. So rather than choose a metric ahead of time, say a Euclidean metric or a cosine distance or a Mahalanobis statistical type distance, the metric is learned from the training data. And by learning the deep embedding simultaneously with this deep nonlinear metric, the relational network can better identify matched, mismatched pairs. So we'll have next, this is from the paper, the visualization of kind of why it works well. So on the top two diagrams, we have the vectors projected. So this is the embeddings, and the embeddings are multi-dimensional, high-dimensional. So we have projected them down using principal component analysis to 2 dimensions so they can be plotted. So this yellow circle here is the query image. And the cyan circles are matching images in terms of the class. And the magenta are mismatched in terms of the class. And so this is another query. So we have another query vector plotted in 2 dimensions, the yellow here, and that it also has a set of vectors. So if you look at that, you'll see that it would be difficult to use, say, something like a nearest neighbor with a Euclidean distance to do well at this level, especially on the right. They're not well clustered at this level in the network. Whereas if we visualize the data that comes out of the relational portion of the network, it demonstrates much cleaner clustering or division between matched and mismatched samples. So what they've done is, I believe that this is an 8-dimensional data at this point in the network. So if you think of it as an embedding of these concatenated vectors, they end up being 8-dimensional. And again, their principal components are analyzed, and the top 2 are used to display 2. So as you can see, like you could draw a line here or here and cleanly separate the matched and mismatched points. So that would indicate that it is much, that this deep nonlinear portion of the relational network does a good job of separating the data. So the conclusion is this relational network was proposed to do this C-way K-shot learning. The relational network learns an embedding and a deep nonlinear metric for comparing query and sample objects. This episode training is used, a mini batch-like technique that's modeled after the target distribution. The relational network is simpler and more efficient than other C-way, K-shot methods. It seems as if it is state-of-the-art for a lot of reasons. The performance, as well as its simplicity. So one thing that I thought I would do as well is, just a moment, let me share something else here. Let's see if I can do this with my desktop, if I can do that. So if I look at,